there is another characteristics of the laser, and that is some of the lasers are pulsed lasers. What you do is basically compress the energy of the output within a short interval of time so as to create a burst of energy from the laser. And one utilizes special techniques to achieve this compression of the energy in a small period of time. So I'm going to briefly mention about this aspect, which is creation of short pulses, right? This is another characteristic of lasers. So typically the pulse duration TP, which characterizes the extent in time of the pulse, it is basically equal to the inverse of the bandwidth. And this is achieved through a process called mode locking, which we will deal with in the later part of the course when we look at time dependent output. Um, Now there are variety of kinds of lasers, and hence there is a huge range of possible bandwidths. So typically for gas lasers, for example, the helium neon, argon ion, there are multiple gas lasers. The pulse width typically ranges in the time scales of nanosecond, right, which is 10 to the power of minus 9 of a second. In contrast, if you look at solid state lasers, okay, and particularly if you look at titanium sapphire laser, in that case the bandwidth is actually pretty large. It's about 10 to the power of 14 hertz. So if one undertakes mode locking in such a laser, one can get time scales is about tens of femtoseconds, right? Where a femtosecond is equal to 10 power minus 15th of a second. On one hand, we talked about monochromaticity, where what you have done is to concentrate the energy at a particular frequency, resulting in an extremely narrow bandwidth about that frequency. In contrast, a short duration pulse is energy concentration not in frequency but in time, which is precisely the inverse of it. So here you are looking at a time scale, and shorter the time scale you are able to put in energy, you will create a shorter pulse. We will not dwell too much on the creation of short pulses, but I can tell you that it's an extremely important area. One can utilize these tools to probe, for example, chemical reactions as they happen, with a wherein you probe the chemical reaction stroboscopically in femtosecond timescales. So you're literally freezing, you're literally tracking the molecule as it undertakes as it undertakes the chemical reaction, and you're essentially taking frozen photographs of that at the scales of femtoseconds. The creation of short pulses in itself is a very important area of research and immensely challenging. A small note that we are able to measure with such short pulses time scales of the order of attoseconds, which is 1,000 times smaller than a femtosecond. We are looking at time scales of 10 power minus 18 of a second. That is the level of sophistication these short pulse lasers have come to, and they open new vistas of probing physical phenomena. So now that we have looked at various aspects of the laser, for example, we have looked at monochromaticity, we have looked at coherence, we have looked at directionality, right? We have looked at intensity, the power itself. So if you want to now characterize a laser source in contrast to any other terrestrial source, so there is a nice parameter that one can define, which is called the spectral brightness of a source. And if you compare this spectral brightness with any other source, you will quickly realize the kind of concentration of energies that laser is able to provide. So let's build this up. So first let me define a few things. For example, when we look at intensity, intensity is defined as power per unit area, right? So now if you look at spectral intensity, uh, which is intensity, but we are looking at from the perspective of how much intensity is within a bandwidth delta nu. So this quantity will be the intensity per bandwidth. So that is how you define spectral intensity. Now when we talk about spectral brightness, so our definition for spectral brightness is basically P, which is power per unit area per unit bandwidth per solid angle. You are looking at the aperture associated with the laser from which radiation is coming out. You are interested in the solid angle this makes. You are interested in the power that comes in and how is that shared across this area. You're also including in this the bandwidth within which this energy is contained, right? So let us just calculate this for a simple helium neon laser that you typically see in your lab. So I'll put in some numbers. So for a helium neon laser, you know that this laser operates at 632.8 nanometers. This is the wavelength. This is a wavelength I would expect you to remember. And let's say we are looking at a power of 1 milliwatt. Let us assume that the bandwidth of the laser is about 10 to the power of 4 hertz, which is 10 kilohertz. So now let me quickly recall how you deal with this area times the solid angle. You will remember that we just had a discussion on spatial coherence where we mentioned that the angular size of the source is related to the area and the wavelength of the system. So given diffraction, which is the phenomena that underlies this widening of the wave when you try to confine a wave within an area. So as you confine the wave within, for example, this area, you are actually limiting the extent of the wave, and hence the wave would uh, expand. And this expansion is characteristic uh, of the light itself or the wave itself, and the spatial characteristics of the wave, which is captured by the wavelength, is what comes into play. Given that my laser is well made, the only angular expansion that arises from a well-made laser uh, is arising only due to diffraction and nothing else. So this particular product, which is governed basically by diffraction, can be written down in the following fashion: that my delta omega, which is my solid angle with which a wave that is confined within an area A comes out, is actually goes like lambda square by A, right? So given that the area is smaller and smaller, the solid angle with which it expands is going to be wider and wider. Similarly, for larger wavelengths, the solid angle is large. For smaller wavelengths, the solid angle is small. So this arises purely out of diffraction, right? So we will use that here, and imagine that our helium neon laser is well made. That would mean that my in the denominator, where they have a product of A times delta omega, I can take this as 632.8 nanometer whole square, which is simply roughly 3.9 into 10 to the power of minus 9 centimeter square. I'm keeping, typically we do measure intensities in watts per centimeter square, so milliwatts per centimeter square. That's why I'm using centimeter square. So I can write down my spectral brightness. Okay, this is beta nu, which is the symbol for it, which is power per unit area per bandwidth per solid angle. This is essentially 1 milliwatt, is 10 power minus 3. All right, and then I have 3.9 into 10 power of minus 9 centimeters square, which is A times delta omega, and my bandwidth of 10 power of 4 hertz. If you calculate this, you will quickly see that this number comes out to be around 25 watts, right, per centimeter square per sterdian. So now let us undertake the same exercise for sunlight and calculate the spectral brightness of the sun. So as you know, this is something that you might have learned very early on in your undergraduation. One talks about the black body radiation formula. That is, we consider sun to be a black body where the surface temperature of the sun is about 6000 Kelvin. So given this temperature, it has a very characteristic emission that looks like that. And given this is characteristic of a particular temperature T, and you see that the peak, as you know, is in the visible for our sun and the yellow-green region of the spectrum. So the black body radiation, it basically gives you the energy density. The spectral energy density was actually derived by Planck, and this is the famous formula by Planck, which also led to the birth of quantum mechanics, because he had to consider in this situation. So he had to quantize energy of the corresponding atoms that lead to this thermal emission, and that is what led to this formula. I will not get into the details of this, but you can read this in any modern physics book. And this spectral energy density, rho of nu, the famous formula 8 pi nu squared by c cube, h nu by e to the power of h nu by kbt minus 1. And clearly this is energy density or spectral energy density. So this is in joules per centimeter cube per hertz, right? Spectral energy density. So imagine that I plot this same function above as a function of frequency now. So in that case, I would get something like that. And you see that when I talk about a range, for example, d nu, so my rho nu d nu is precisely the you see the area under this bell-shaped curve. And if I just integrate this from 0 to infinity, I would get the total radiation, that is the total emission. Let us see from here how do we go about calculating the spectral intensity, because what we have is spectral energy density. So if you see clearly, you have got energy density which is confined within a volume, and imagine that that energy travels with a speed which is c, right? There's an electromagnetic wave, so it travels with the speed c. So one can write down the spectral intensity as the product of the rho of nu with c, right? This will give me spectral intensity. Clearly you see that now if let's keep track of the units. I had joule per centimeter cube per hertz, and now I multiplied this by centimeter per second, right? And now for getting the spectral brightness, all that I require is to consider my spectral intensity and look at the solid angle with which the intensity is emitted. It is emitting in all the 4 pi directions. So I'm keeping track of the units on the right. So what I get is joule per second, right? Which is my, which is watts per centimeter square per hertz. So in our situation, the beta nu for the sun will simply come out to be C times rho times 4 pi, which is simply this object, uh, twice nu square. Remember, the 4 pi takes away the factor 8 pi there, so you are left with a 2 by c cube h nu by e to the power of h nu by kbt minus 1, right? So this is the kind of expression that you get. Now I just need to calculate, put numbers to this. So I'll put in the parameters. So let's look at the temperature of the sun. T is 6000 Kelvin, which you know is simply 20 times 300 Kelvin, right? So, and I told you that kBT for room temperature was 1/40th of an eV, right? This was, so this will be 1/40th times 20 electron volt, which just happens to be 5. The exponent will come out to be just 5. And then I have similar considerations when I'm looking at nu. I'm looking at 10 to the power of 14 hertz, right? So one can basically put in all these numbers. So I leave that as an exercise to you, but you will quickly see that your beta nu for the sun will come out to be 1.5 into 10 to the power of minus 12 watts per centimeter square per sterdian per hertz. So let's compare this number with what we had got earlier for the helium neon laser, which is just a 1 milliwatt helium neon laser. That was 25 watts per centimeter square per sterdian per hertz. Here you have 10 power minus 12. So literally you have 15 orders of magnitude difference between just a simple laser in comparison to the sun. Beta for the laser can although go from 10 to 10 power of 8 watts per centimeter square sterdian hertz quite easily. And of course we have extremely high power laser where this number can be petawatts. We are not going to talk about that, but certainly this can get larger and larger. At the end of the discussion, I want to basically emphasize that it is extremely dangerous to look into the laser. When we are looking at a 40-watt lamp and we are looking at a 1 milliwatt laser, it is the spectral brightness that is damaging to the eye. So as a note of caution, in the next semester when you are doing experiments in the laser lab, be very careful not to allow laser light, to even the stray reflection of a laser light, fall into your eye. Remember, the back reflection from a glass itself is about 4%. So if you are looking at 4% of 25 watts per centimeter square per sterdian per hertz, which again is going to be a very large number, still continue to remain 12 orders of magnitude higher than that from the sun. But again, because of our ability to compress energy into such spatial as well as temporal time intervals, so this is what makes laser such a powerful tool to do science.